Hello everybody, my name is Sam, welcome to Rust Fasttrack. Today we're going to be looking at types, specifically data types, the primitive data types. Now, there are a lot of things that go into what Rust sort of considers to be part of its type system, and to summarize those, there is the data type itself, which is the type of the data being stored. There is the mutability of it, whether it can be changed. There is the lifetime of it, how long it lives for, and there is the ownership of it, who actually has control of this data. Now, over the next 4 episodes I'm going to be explaining those, but we're going to start here with primitive types and some of the types exposed by default in Rust. So, here are the primitive types. They are array, which is what you'd expect. It is a fixed array of type T of n units. So it is essentially, you say, I have this many things, and I've got T of them. Now, two-dimensional arrays aren't a thing. That's a thing to note. You can do jagged arrays, though that would be ill-advised. I would say the correct way to do it is to define an array of type, of length of your x times your y, and then pass it using some algebra. But anyway, there's bool, which is the Boolean type. This can be either true or false. There's char, which is the character type, which is a Unicode scalar value, which is a fancy way of saying that it is an unsigned to U8, basically, I believe. We'll see. What's it wrap? Char is a Unicode scalar value. A char can always be safely cast to a U32. There you go. So you can bring it in from U32. Anyway, F32 is a 32-bit floating point value. So floats is anything with a decimal point, and then 64-bit version. Then you've got a 16-bit signed integer, which means, do they have a summary? They don't. It's 15-bit signed integers, which means it can be positive or negative. Then there's the 32 and 64 and 8-bit. Then there is isize, which is I believe isize is, it's a generic integer, a generic signed integer that I believe takes the maximum size of your CPU. I might be wrong there, but isize isn't really used that much. usize is, but I believe isize is just whatever the biggest, the biggest thing you can have is. Yeah. Pointer. Operations on unsafe pointers, dereft constant T and dereft mute T. Pointers are generally only used when you're dealing with bringing unsafe code in to Rust. For example, casting variables in an unsafe way. Slice. So slice is well, it's kind of what it sounds like. It's a slice. It's a subset. It's a bit like a array. In fact, an array can be cut up into slices, but it doesn't have a fixed length. And I believe it's an anonymous type, which means you can't define something as a type slice, but you can define something. Yeah, here. So here you can see a string slice. Slices are denoted by essentially ampersand square brackets, and then the thing that they're referencing inside. So here, there's an int slice there. Yeah. Slices. They're kind of hard to explain. We'll go into more detail in them later. There'll probably be a whole episode just on slices. Strut. Strut is for string literals, so that is the type of this. Specifically, these are and static strut, which it says here. When you use it in a literal. Yeah. Tuples. These magical bracketed values that can have pretty much, like, you stick a bunch of data in them. They're magic. That's all there is to them. Magic and voodoo. U16 is an unsigned 16-bit. This means it's only positive. U32, U64, U8, or what you would expect. And then usize is whatever the biggest is. I believe I'm correct in saying that. There's a ton of modules, and that's it. So let's look at each of these types a bit. So let's start with integers. So I actually want to clear that and delete that. Okay, let's get text open. here we are. We're going to look at them one at a time, and we're going to look at them how I see fit. So first of all, there is no way to output the type of something cleanly. There is an unsafe bit of code that does it, but there's no way to do it safely, and that means that the best way is to deliberately write some code that doesn't compile, let the compiler throw an error, and just read what type it is there. So let's start with f32. So we're going to say let x of type f32 equal 3.2. Then we will say let's do the whole alphabet. A of type f64. This is also just going to look like the same. It can just store more. Next up, we can have let C of I16. Now this has to be a value less than 2 to the 16, half of that. So, God, what even is that? 2 to the 16 divided by 2, 32768, I believe. I may be wrong. It might not go to exactly half but it's signed. So yeah, half of that. So that can go as high as that, which means if you do a huge number, that shouldn't compile, or it will maybe throw a runtime error. Yeah. So if we show the command prompt quickly, you see we get this. Let me turn off unused variables because they're all going to be unused. Hold on, I'll show you how to do that quickly. So all you've got to do is put here. I believe it's ignore, or is it allow? I think it might be allow. Yeah, you do a crate level allow. So we say allow unused variables. I believe that should do it. So the compiler no longer complains to us about unused variables. No. I think I might need the, sorry. Why are we... Oh, variable, my bad. Sorry, just fixing it. There we go. Now we only get the error we care about. So, cargo run. Runs fine, but when we build it, we should get a warning. No. Why do we no longer get a warning? We were getting a warning a second ago. There we go. So we say literal out of range for I16. So it's trying to set, because this line of code, there's a risk of overflow there. So as you can see, it's got to be a lot smaller. So I'm going to make it a lot smaller. I'm going to make it comfortably within the range of an I16. And then there is I32, which can be bigger. I64, which can be even bigger. I mean, I'm nowhere near the limits of what they can be. I'm just showing you sort of the scale. Like this can also be bigger. More detailed, sorry, for a float. Not necessarily bigger. Okay, and then there's I8. So I8 can only be tiny. I8 is absolutely tiny. Only 8 bits to work with there. And then iSize, which is as big as it'll let it go. So EFG iSize equal, and that should comfortably fit. And I believe if we build that, it should throw no potentially too big warnings. Yeah, I believe this could go ridiculously big in theory, because iSize on this machine should be 64 bits, and that's a big number. There you go. Int literal is too large. Okay, so it did hit an error. It didn't compile because it's too large. But I mean, it's some stupidly big number you can go up to with those integers. I did just spam it, so I've made it a bit smaller, but still significantly big. So you can see that those are going to be as big as i64s basically on this machine. But yeah, okay, let's do the unsigned now. So let H is an unsigned 32-bit. Let's make some of these negative because we can, just to show that you can have negatives in those, but you cannot have negatives in these. Unsigned 64, J unsigned 8, and let's do unsigned 16, which is tiny and is usize, which is again going to be bloody massive. And bigger than isize because it's unsigned, which means it can be double the value, essentially. Right. Okay, next let's do arrays. So let's say let q, jkl, let's go l, of type i32 8 equals 1, 2, 3, 4, 5, 6, 7, 8. There we go, that's an array. Then let's say a bool. And this can be true, it can be false. Let's go true, let's say positive. Could have a car. There we go, we got a car. We could have a slice. What should we have a slice of? Let's have a slice of I32. I believe that works. Yep, it does, okay. So it's a bit like an array, but it can be any length because it's just a slice, which is literally just a pointer to an array. This pointer here essentially says point to some array with a start value and an end value. I mean, I could rewrite this and say we want to point to L, but we only want the first 3. I believe that would have the same first 3, maybe? 0 ... 3, sorry. They start at 0. Like in all sensible languages. And I believe that has the exact same effect. Like if I go the built okay, if I edit the code a bit and we just compare these, so we'll say let P and I32 equal, and then just, so I believe I can just get away with doing this. So we want to say O and P are the same thing. Notice we're not saying that they are exactly the same, but they are the same. I hope this works. I could get false back, or we could get nothing back. Oh, I just built cargo run. True, yeah. So you can see O and P are the exact same thing. So all I did was I said take a slice of L for values 0 to 3, where the first one is inclusive and the last one's not. So we go 0, 1, 2, don't take that one. And then down here, we built up a new slice. Okay. Q, what's left? Strut. Now this probably won't compile. It might. Give it the benefit of the doubt. Come on, Rust compiler, work with me here. Well, hey! Mismatch type, expected str found, and static str. So basically, string literals are always static. Now static is a lifetime, and I will talk about lifetimes in a future future one of these episodes coming up very shortly, because it's part of the 4 things I want to talk about when dealing with variable types. But all you need to worry about is static means that this is essentially known throughout the entire program. This string, I mean, I can show you what the assembly looks like for static. Hold on. Let's get the wonderful internet up again. So this is play Rust. I'm just going to use it to say let test be some static string of type Bob. And it's going to compile, it's not going to do anything, but if we actually look at the assembly code, you will see that in here somewhere should be Bob. There we go. So here you can see this, you can't see it because I've monged up. Down here, so Strut 701 is how it's defined in the assembly. It's defined with the ASCII value Bob of size from, basically this size means we want to take the pointer that is Strut 701, which is itself, and go forward 3, and then this means that it's actually storing this value. Its type is const 702, which is defined down here as being quad Strut 701 size of const 702 16, which is the size of this section, and it's defined as being a note on the GNU stack. Anyway, and then section, that's all data allocation. But you can see this is just exists here. I believe if I say an I32 and do this, it should have a different behavior. Yeah, so here you can see 153 here is defined as const 701, long 153, size const, it's 4 bits long, that's the number of bits needed to store this, yeah. Yeah, so that's sort of how these are done in the assembly. But because this, you see, this isn't a string that then goes through another thing. It's just defined slightly differently. I could make it static if I made it a reference and I just said this. But yeah, let's do that. Yeah, I didn't think I would like that, but no. That's just a difference in the actual assembled code. I'll talk more about lifetimes in a future video, hopefully very shortly. I think that's everything. Pointers. Ugh. Okay. Yeah. No. Yeah. Okay. So a pointer has a type that looks like this, asterisk const, and we want a I32 version of it. And then we're just going to say to some reference of like 8, I believe that will compile. Yeah, it compiled and ran. You can see, nothing actually happened there. These are really hard to explain. I will explain pointers. They will have the whole episode to themselves. I'm not going to get into it now. So here you can see all the primitive types. Now, there are some things to note. In Rust, you've got 2 places that memory goes, either onto the stack, which is this very fast popping on and off memory, and the heap, which is this huge bundle of memory that you saw. I showed you the heap a second ago. We looked at Bob on this. We looked at Bob allocated in the program in some heap memory that was referenced to, and all of that nice stuff. Anyway, oh no, that would have been pushed onto the stack. But anyway, ignoring all that, to put something in the heap in Rust, you do this very magical thing. I'm just going to open the docs and double check I'm not talking out of my arse. And I've got to reset that again. There we go. Box. A pointer type for heap allocation. There is module level allocation, but basically what it means is if you want something to be on the heap, by default all these primitive types are going to end up on the stack. But let's say we want S to be a I32, but we want it on the heap, because stacked memory is very quick, heaped memory is very slow, but stacked memory is a limited resource. Let's say we don't want this to just be filling up our limited resource for whatever reason. I believe that this will work out of the box. Box should infer itself because it just becomes a special kinds type of reference. Oh no, what don't you like? 1 second. I'll let you have a look at that. Let's find out what it doesn't like. It does not like expect a box. Okay, so you do have to box it manually? Yeah, you do, sorry. We have to say we want to create a new box. Boom, there we go, a new box around this. And that can be any type of tool, because box new is a magical function that takes a reference to type T, which can be literally anything. Type T is Rust's magic way of saying anything can go here. Anyway, so that takes that in. Another thing you might want is vectors. Now vectors are what might be called lists in other languages. It's essentially a way of giving you an array. So T we might have as a vector of I32s, and then we might create it as a vector of 8 to 91. This macro here, all this macro is doing, I believe, and we'll check this, but I believe in theory this macro expands to something that looks roughly like this. So it will say let T equal new, where T is of Vec, and then it will just push 8, and then it will push 2, and then 91, and then it just returns that. We can double check that. I have genuinely no idea if that's what it does. That's what I've always assumed it does. Let's find out. The beauty of Rust is it's incredibly easy to check the docs. So, I don't know, Vec. No, I want the Vec macro. There we go, Vec macro. Oh my god, that is ugly. Okay. Wow, that is an ugly function. Takes an element, an expression. I'm not going to try and understand that. I probably could if I sat down and spent ages. It's not worth it. I'm going to assume it does what I thought, and I'm just going to pretend that that magical nonsense turns it into what I thought. Maybe someone with a better understanding of Rust on a compiler level will actually tell me what this does, but I mean, yeah, it makes a vector. So boxes you will need if you want to have memory allocated to the heap. Vectors are heap allocated as well. So that's another way, but vectors, I mean, they have a length. They actually allocate with a specific, like a box will only allocate on the heap the space it needs, so this will allocate I32. A vec will allocate a ton, and then if it starts getting too big, it will just shift the whole thing over to a new, like it'll allocate a new, take a new allocation region, fill that up. Let's do a quick diagram. So let's say you wanted let's say you had, it allocated itself 4 boxes, and you fill these, sorry, 3 boxes, and you go 1, 2, 3, and you want to add 4. Then what it's going to do is you've got all this other data. Maybe there's some random nonsense in these, like, just random other nonsense. And then there's some more free space. And it's going to, okay, we definitely need 4. Let's just allocate some more. Move over what we've already got and deallocate this. Deallocation, I'm pretty sure it will just sit there in memory, but just as dead memory. We'll reallocate this, and we'll make sure that there's some extra space protected afterwards that can't be allocated by anything else. That's how that works, which just means that I believe it's vec with allocation or something like that. Let's find out. Let's have a look. We'll go read the docs. Let's make it so you can see it. There you go. With capacity, there you go. And that takes a usize and then constructs an empty vec with a specified capacity, and if you ever overflow that, it will automatically reallocate to a larger capacity, is how I understand vectors work. They have a ton of really cool functions, but most of their mechanics come from turning them into an iterator and then doing stuff on that. I will explain iterators in a later date, and I won't be in this episode because they are not a type, they are a trait, and traits are outside the scope of this episode. I'm pretty sure I'm cleaning up here. There's not much else you need to know for basic Rust code as far as types go. Here you've got all the primitives and 2 slightly more advanced ones to do with heap allocation and essentially arrays of unknown size. I'm just trying to think if there's anything else before I sign off. And I'm not thinking of anything. So if I think of another useful type that might be worth you knowing, I will let you know. But for now, I believe that's it. So this has been 25 minutes-ish on types. And the next episode, I shall be looking at, probably, we'll tackle mutability. So yeah, here's but this has been episode 2. Thank you for watching, I guess.